right now I'm working as a professor at Madurai Kamaraj University, India. Meanwhile, I'm visiting now Institute of Chemical Technology, Universidad Politécnica de Valencia, for about 2 months. So I just wanted to make use of this opportunity to present some of our results to this conference. So as the title conveys, so basically our aim is to make use of metal-organic frameworks as heterogeneous photocatalysts for the generation of fuels. So basically, we wanted to use these materials to make more visible active to generate fuels like hydrogen and methane. So we wanted to make use of 2 or 3 well-known reactions. One is the hydrogen evolution reaction or CO2 photomethanation. So conversion of CO2 in the presence of hydrogen to methane. And the next reaction will be overall water splitting. So we wanted to use water to hydrogen oxygen. So last year, these 3 scientists were awarded with the Nobel Prize. So this is Susumu Kitawa, Japan, and Richard Robinson and Amarajothi. So these 3 people were simultaneously developing this material somewhere from 1995 to 2000. And last year, they were awarded the Nobel Prize. So one of his papers, Susumu Kitawa, probably it has nearly 8,000 citations because all the people who wanted to write any manuscripts with MOF. So always we cite him because this was one of the pioneering work of MOF. Meanwhile, Amarajothi introduced a series. First MOF was MOF 5. So this was well used for various applications. And when I came to Valencia in 2008, that was the time people were thinking to use this material for heterogeneous catalysts. So nobody was believing that these materials can be used as heterogeneous catalysts, but we were the first to demonstrate that these MOFs can be used as a solid catalyst, especially for performing Lewis acid-based catalysts or redox catalysts. So we were first group to report in 2009, and earlier there were only 2 reports. By one of the reports from Stephen Pascal from Germany, and the second report was from Belgium by Pascal. So then we reported in 2009 using MOF heterogeneous catalyst. So what are metal-organic frameworks? Basically, they are crystalline porous materials which are constructed from the coordination of a metal center with organic linker, and you will get a very beautiful and highly ordered crystalline materials which has a metal center and connected by organic ligands. So one can play around with organic liquor. So you can introduce a number of functionalities here. So if you put acid groups, that is going to behave as acids. If you are going to introduce a basic sites like NH2, that is going to behave as a basic sites. And basically one can easily tune the properties of MOFs by designing an appropriate ligand. Also, you can vary the metal center starting from a number of you can use any metal from the periodic table, and of course you will have a different set of MOF which have a wide range of properties like highly crystalline, multiple affinity, electronic optical properties, tunable topography, and as a high porosity which is essential for performing organic reactions in catalysis, and also high surface area. So far we have been working on heterogeneous catalysts, but recently we moved our interest to photocatalysts. And as I commented, we wanted to use MOFs as photocatalysts for 3 reactions. One is a hydrogen evolution reaction, CO2 photomethanation, and overall water splitting. So for any catalyst to be highly efficient photocatalyst, so it has to have either to improve the photo absorption through metal doping, and also the MOFs can be fabricated for enhancing charge kinetic, especially we want to separate the holes and electrons, and then to enhance or to create more active sites. So one has to create defective sites and also functionalization in the ligand, because it has to absorb the visible light and it has to create more number of active sites. So these are some of the basic requirements in the MOF catalyst. So this is my, I can say my boss or my collaborator. So I started my first postdoc with him is Professor Amarajothi Dhakshinamoorthy. So who is working as a professor at Institute of Chemical Technology, and he reported in 2010 the first example of reporting MOF for photocatalysts. So he just reported UiO 66 for the generation of hydrogen, and this was his first work. But this reaction was reported in the process of sacrificial agents like methanol production per sulfate. But our interest is to use MOF for these two reactions, hydrogen evolution reaction and oxygen evolution reaction. And as I said, the first hydrogen evolution reaction was reported in 2010, and later nickel coordinated to aluminum based MOF was reported in 2017 for overall water splitting. So this was reported in inorganic. And lately, the next example appeared like constructing two MOFs, so one MOF as a core, the other MOF as a shell. So this MOF was constructed for the hydrogen evolution reaction, and this was reported in ACS applied materials interfaces. So the key point here is that if you want to develop a MOF based photocatalyst, so one has to consider to design an appropriate band alignment in the MOF. So you have to play around with metal center or ligands or functionalized ligands, and then to enhance the visible light absorption. So basically, if a photocatalyst is not going to absorb the light, so obviously no steps are going to occur. And obviously, the next one is to increase the photo-induced charge separation. So unless we are going to separate the holes and electrons, if we are going to recombine very shortly, so obviously the photochemical reactions are not going to occur. So these are some of the basic parameters which has to be taken care of while developing MOF-based photocatalysts. And I will show you some of the recent examples where these parameters were taken into consideration, and we have developed series of photocatalysts which are going to exhibit activities in these reactions. So recently we have written a chemical reviews based on metal-organic frameworks as photocatalysts for solar-driven overall water splitting. So if some of you are interested, you can just have a look to this article. So the first example, so we have selected these catalysts. So we have UiO 66 zirconium amino. So this is the amino. These amino groups are functionalized in the 1,4-benzene dihydroxylic acid linker. And here you have zirconium 4 plus as the metal center. And in this case, UiO 66 cerium. So instead of zirconium, you have cerium metal. So this is zirconium 4 plus. This is cerium 4 plus. So we have prepared series of samples. So this is just pure UiO 66 zirconium amino, and this is UiO 66 cerium. And in this case, this is zirconium is going to be as a core, UiO 66 cerium is going to be as a shell, and these 225, this is the amount. So this is the 200 milligram and this is the 25 milligram. So again, in this case, UiO 66 is going to be in the core, and this is going to be shell. And the fourth one we have changed. So we put cerium in the core and zirconium as the shell. So typically we have two set of MOFs. One is going to occupy the core, the other one is going to occupy the shell. So this is something like MOF on MOF. So people call it in the literature. So you have two set of photocatalysts, and we have selected or we have decorated one as a core, the other one is a shell, and we wanted to perform the activity of the solid in the overall water splitting. So this is imagine that catalyst, the outer side is another catalyst. So you can see that we wanted to make use of visible light or solar as a source of light to perform these photocatalytic reactions. So after the preparation of these photocatalysts, these catalysts were characterized by powder XRD, infrared, X-ray photoelectron spectroscopy, TGA, SEM, and TEM techniques to make sure that there are two solids exhibit as core and shell. So this is a powder XRD which clearly shows the existence of this core peaks for UiO 66 zirconium and the cerium, and this is the expanded version, and you can see that as these are the peaks corresponding to UiO zirconium, and this is corresponding to the cerium. So since there is a slight difference in the identity of zirconium 4 plus and cerium 4 plus, there are slight shift in the peaks, but otherwise they are crystalline and they are corresponding to the respective materials. So after the synthesis, we just deposited the platinum nanoparticles and lead nitrate and nanoparticles to make sure that which is which MOF is in the core, which MOF is in the shell. So these nanoparticles were deposited, and these are the corresponding elemental mapping, which shows that inside we have cerium and outside we have the zirconium. And this is this is the sample for UiO60 zirconium amino 25 at UiO66 cerium. So this sample was selected for STEM analysis, and we have selected one particle, and then we have just analyzed the cross section, and you can see that the cerium was deposited on the outer surface with a thickness of 4.6 nanometer, and this entire is the zirconium, which occupies about 170 to 180 nanometer. So this clearly explains that we have UiO66 zirconium amino as the core solid, and the shell was decorated with the UiO66 cerium. So after the synthesis, we just wanted to check the activity of the solid. So we have tested the performance of hydrogen evolution reaction here. So this clearly shows the activity of all the 4 samples. So this is just pure UiO60 zirconium amino, and this is cerium, and this is with a 200, that is inside UiO core, and this is outside shell, and this is the solid which exhibited the highest activity. So the blue shows the evolution of hydrogen, and this is the oxygen, and this solid exhibited the highest activity. And also the electronic contact between these 2 solids were confirmed by U-visible and redoxant test by TEM analysis, and the efficient photo-induced charge separation was confirmed by photoluminescence spectroscopy. And one of the important experiments was when we check the physical mix of these 2 MOFs. So these samples, except these 2, the B and C correspond to the core shell type. But if you just take this UiO66 zirconium amino and UiO66 cerium, if you just take these 2 solids and physically mix, instead of making a core shell, you just take those 2 solids and then physically mix and then perform the reaction, and the activity was almost similar to this. So there was no much improvement, and this was one of the important control experiments to make sure that we have generated core shell type of MOF on MOF solid instead of just physical mixture, and the activity was superior in this case, and which confirms or which reinforces our characterization results. And obviously we wanted to check the stability of the solid, because always people say that upon irradiation MOF is not stable, so it loses its structural stability. But we wanted to make sure that the solid was reused for 6 cycles, and each cycle corresponds to 22 hours per cycle. So we have shown that the solids exhibit more or less identical activity for the generation of hydrogen as well as oxygen. And then this is the XRT for the fresh sample and after 6 times used sample. And also we have checked the leaching of zirconium and leaching of cerium, and under our condition the solid was really active, and there was no leaching of zirconium, but a slight amount of cerium was leached. And basically this is another evidence that cerium was decorated on the outer surface, and probably upon irradiation it tried to lose some activity, but still the activity, activity was very good. So in order to understand the photo-induced charge separation, so we have selected 2 probe molecules. One is called methyl halogen as 1 electron acceptor, and the other one is tetramethylphenylene diamine. So this, upon irradiation, so we have taken this photocatalyst. So upon irradiation, this has turned to this Me plus, so accepting 1 electron, and then the order of photocatalytic activity exactly matches with this irradiation. So the best sample exhibited higher charge separation, and you could see that the higher intensity was obtained for this. The same results were obtained for electron donor like tetramethylphenyl diamine, and you can see that the similar activity was observed for this also. And in the previous slide I showed the results of overall water splitting, and here we perform the individual activity, that is, this is for hydrogen evolution reaction, and this is for oxygen evolution reaction, and again we achieved a similar trend. So the best sample was UiO66 zirconium amino 25 as a core, surrounded by UiO66 cerium as a shell, so MOF solid, and this was the active subcatalyst for overall water splitting, as well as for hydrogen evolution reaction, as well as for oxygen evolution reaction. So this is yet another evidence to show that the faster decay lifetime obtained for this solid compared to the other solids can be attributed to the more efficient photo-induced star separation. And this is one of the key experiment to reinforce our experimental results. So we wanted to compare our data with the literature data. So this table clearly shows that our material shows very high activity after 22 hours, and we don't use because there is another paper. So this paper, this is a porphyrin based MOF which exhibits 836 and 418. This is after 72 hours, and here they have used a platinum porphyrin and the ruthenium bipolar complex and iridium bipolar complex. So the system was a little bit complex here. Whereas in this case, we have just taken a very simple catalyst and it has given better activity. So this work was published in SES Energy and Fuels. So I will now move on to the next reaction, namely the CO2 photomethanation. So as you are aware, the negative impact of this CO2, so more than 80% of world primary energy comes from the fossil fuels. Obviously, so you can see the effective of negative impact of CO2. So as I commented previously in the introduction part, so our aim was to make use of MOF for the CO2 methanation. So obviously this reaction has been reported in the literature by employing very high temperatures. So typically people use more than 550 degrees centigrade, and also they use heterogeneous catalysts like ruthenium or nickel nanoparticles. So this is well known as a Sabatier reaction. And one of the possible alternatives is to reduce the temperature or to employ milder reaction conditions. So typically to reduce the temperature or pressure of hydrogen gas. And obviously when these reaction conditions were altered, so obviously there was a kind of a problem like sintering and catalytic deactivation. And these are some of the catalysts which has been reported for these reactions like TiO2, graphenes and carbon nitrides, perovskites. So this is one of the well-known materials. And the co-catalysts typically employed for these reactions, ruthenium or palladium nickel or copper. And when we started this project, so in 2019, the first example we reported was the zinc-based MOF. The activity was only 1.09 micromole per gram per hour at 215 degrees centigrade after 24 hours. So this was the first example for CO2 photomethanation, and we were not very much impressive with these results because the activity was almost nothing. But then we wanted to develop, because people say that always zinc-based MOFs are not good for even for catalysis, because first of all there is an issue on stability, and the second one is zinc is not very stable. So we have prepared, we have taken Mil-125 titanium amino. So we have developed, we have loaded ruthenium-based catalyst, so with different weight percentages, and it was characterized by powder XRD, and again it was characterized by SEM analysis. And this is a TEM analysis. So here I just wanted to conclude that upon increasing the loading of ruthenium, the particle size was more or less same or identical. It did not increase much. So again, this was confirmed by diffuse reflectance, and this is the tau plot to calculate the energy band level diagram. So here you can see that the activity was compared. So this is from 1 weight percentage to the 10 weight percentage. As the ruthenium loading increases, the methane generation was also increased. And here we just performed the chemistry option, physics option. This experiment was to conclude that ruthenium is inside and which is activating the CO2 which by means of chemistry option. So here also you can see that as the temperature increases, the activity was also very high at very high temperature, and almost you can get 15 millimole per gram per hour. So we have demonstrated the efficiency of this catalyst by performing 10 consecutive cycles, and the catalyst was almost identical. You can see that the results were very impressive, and we have also characterized by XRD. So the XRD did not show any changes in the structural integrity, and again the stability was also confirmed by XPS. And this is the TM analysis of after the catalytic reaction. and there was a slight increase in the ruthenium particle size, but that did not affect much on the catalytic activity. So finally, we also wanted to check the continuous flow experiment with this. So we have developed the in situ photoreactor where we have just introduced a CO2 and a hydrogen. This is the concentration, and we have put this catalyst ruthenium loaded on 125 amino, and then this was connected to the micro GC, and we monitored continuously the formation of methane generation. And this is 150 degree and at 200 degrees centigrade, the activity was more or less good. And this is the XRD of the fresh and reused catalyst, and the stability was also confirmed by TM analysis. So this is the comparison table. So this was published in Chemical Engineering Journal. And recently we reported one MOF, that is MIL 173 zirconium or titanium. So now in the previous example we decorated the ligand, and in this case we just put two metals in the MOF, and this showed roughly about 1.63 millimole per gram per hour. So this activity is even higher. And in another example, we have just loaded ruthenium oxide in nil 1 upon chromium, and which exhibited the record value of 9.2 apparent quantum yield under visible light irradiation. And here the activity was 7.85 millimole per gram per hour. So we have drastically increased from 1.09 micromole to 7.85 millimole per gram per hour, and this is the highest value reported so far in the literature. And we also checked the stability, so it was reusable. There was no change in the XRD with the fresh and reused solids. These were the TM images of the fresh and reused material, and you can also see that XPS did not show any changes. So we have demonstrated that the catalyst with exhibiting very high activity, and it retained its structural integrity with better activity. And I hope now you agree with me that MOF can be used as a heterogeneous photocatalyst for the generation of fuels. And now, especially European Union is investing a lot of money to develop new set of photocatalysts. And in fact, we were involved in this basically to use MOF for hydrogen generation. And Madurai also again another European project where we wanted to make use of sun using MOF as a photocatalyst for the production of methanol. So these two projects were recently completed, and I thank all my collaborators and some of the PhD students whose work were presented here. And thank you very much for your kind attention. So I will be happy to answer some of your questions.
Thank you, Professor, for very interesting talk. We have time for one or two short questions.
I'm sorry, I'm not working in this area. I don't understand the activity numbers in millimole per gram per hour because it is photocatalysis. Where are the photons? I don't see the quantum yield.
No, we measured the so the current quantum yield is calculated, and it has been given for each catalyst.
Okay, you will explain why.
Yes.
Okay, do we have any other questions from the audience? Okay, so maybe I will ask one.
Yeah.
You showed us that you have a very good dispersion of ruthenium oxide on metal organic frameworks. It's quite interesting because you have a relatively high concentration of ruthenium oxide because it was up to 10%.
Yes.
So what was the method for the deposition of this ruthenium oxide?
So this is photo deposition. So we just take the MOF suspension, and then we just add the ruthenium precursor dissolved in a methanol solvent, and then we use usable light to deposit.
Can you further increase the loading of ruthenium oxide and obtain even higher activity? Because you showed that the highest activity was observed for 10% of ruthenium oxide.
So in fact, is it over or
yes.
Okay. Normally, we would like to maintain the weight percentage from 1 to 5%. So we have reached up to 10 weight percentage just to increase the activity, but upon increasing the weight percentage to 15 or 20, did not show any result. or the activity was similar, or even it was little bit lower. Because the particle size, there was a limit. So after a 10%, the particle size was slightly bigger, and like it was also occupying the pores, and the activity was not very much high. So then we decided we stop at 10%.
Because this was the optimal value.
Yes, but if I remember well, we were you wanted to measure the particle size of 1 weight percentage to 10 weight percentage, and luckily upon increasing the weight percentage, there was no much increment in the particle size. It was about 1.141 to 1.48, but it was in the 1.4 nanometer more or less. So it did not increase, but the activity was really good.
Thank you very much. And certificate for you, please. So please come.
Yeah.
Okay, so congratulations, very excellent.
Thank you, Lucas.
Let's say I'll say once more. And
Lucas, we have a certificate for you of being such a wonderful chairman. So this is for you.
thank you. Thank you very much.
And this is the end of this session. We have 10-minute breaks, and after it will be the poster session. Thank you very much. Thank you.
Thank you very much.
Okay, so tomorrow
This is the certificate from the other person who is not attending. Okay.
I will replace those.
So we had some change in the program, but I was not aware that it is so.
It's nice talk. Thank you.
Thank you very much.
Do you want me to go and see this? Yeah, and see things. Okay.
Do you know Professor Natali?
Yes, yes. Can you have a history?
Yes.
Yeah.
Yes. One of the European project.
I know this cluster
Christian said yes.
and for
Photo.
Okay.
Yes.
yeah.
But now she's in Spain,
Yes.
and now she moved to Madrid.
Yeah. She's really very smart.
Yeah.
And very nice too.
So we were working on this project.
Yeah, but you mentioned that the other.
Until things you have flower.
Yeah.